Thank you very much all for attending this session. So I'm Martijn Starmans. I'm a PhD student at Rotterdam, the Netherlands. I'm no radiologist, so please forgive me if I use a bit of odd terms at some points. And I will tell you a little bit about our work of classification of malignant and benign liver tumors using the radiomics approach. So I have no conflicts of interest. So the problem we're addressing here is primary liver cancer, or more specifically, the first time a patient comes into the clinic with symptoms which might identify this. So most of the times we make an MRI, and then the primary task of the radiologist would be to decide whether a tumor is malignant or benign. So this basically determines what's going to happen to the patient. So malignant patients might get referred to tertiary hospitals, or might even get treatment, while patients with benign tumors might get a follow-up or might even be sent home. And the earlier this diagnosis is made correctly, the better the treatment is. So this scoring is rather difficult. You will see that all over the place here, and thereby also subjective. If you ask a different person to score the tumor, you might get a different diagnosis. So there's this need for a better prediction model. So the solution we're proposing here is to use radiomics. So I'm sure most of you have used this term, have heard of this term around here, but let me explain it in a nutshell. So what we do in radiomics, we use imaging, so in this case MRI. Then in the second step we segment a region of interest, so in this case the tumor. Then we extract some features, so these features are characteristics about your tumor. So you can think about the shape of your tumor, the intensity of your tumor, but also more complex measures like texture patterns or heterogeneity. So we do this for patients for which we already know whether these tumors were malignant or benign. And then we can use a data mining method, so for example machine learning, in order to make a model out of this, which can do this prediction for us. So this is in general what radiomics contains. So now we are going to apply it in this study. So we start with the image acquisition. So we acquired a multi-center database. So these scans originate from 54 different institutes of T2-weighted MRI of 190 patients. So you can imagine this data set is quite heterogeneous. There's quite a variety of imaging protocols in here. So all these patients have a pathologically proven HCC, HCA, or FNH. So we have one malignant subtype, HCC, and two benign subtypes. So using this data set, we're going to the second step, so the segmentation. So in this case, a radiologist manually annotated each tumor on the MRIs. So using these region of interest, we're going to extract features. So we extracted over 400 of these characteristics describing the intensity, shape, and texture of these tumors. So then we go into the data mining step, and it's a little bit more complicated. So suppose we start on the left with our images, and we have to develop this radiomics model. So these typically consist of a number of components. So you have different feature extraction methods, you have different feature selection methods, oversampling methods, and machine learning methods. And if you will look around here, you will see there are a lot of radiomics methods. So a lot of different methods, but also a lot of different parameters. So the question raises which method would be most suitable for the problem we're addressing here. So I'm going to use this platform called Voort, a workflow for optimal radiomics classification. I actually have another talk on that in B908, so if you're interested in that, come look over there. So what we did in there is that we collected a lot of different radiomics methods, put them in one platform, and let the platform figure out itself for each application which methods are most suitable. So it tries basically to find the optimal path within this collection of methods and parameters. So we're also going to do that for this study in order to make this classification model. But I do the same in, for example, brain cancer, soft tissue cancer, etc. So if you're interested in that, please come to this other talk. So we did this for the liver study, so I can show you some results. So we have one data set, so that's why we're going to use a cross-validation in order to evaluate how our method performs. So what we do, we split our data set in a training and a test component. On the training, we do this whole optimization and training of the model. And then on the testing, we only evaluate our model. So our model has not seen these test patients during training time. So we get kind of an independent measure of how it performs. And we repeat this process 100 times because we could be lucky the first time that all the easy patients are in the test set. So by repeating this, we hope we get an honest error estimate. So these are the results that we get over here. So this is an ROC curve, the receiver operating characteristic, which I hope many of you are familiar with. But the dotted line is basically guessing. The top left corner is a perfect score. And you can see that our method is closing in on the top left corner. So we have quite a decent performance. And that's also reflected in these measures at the bottom. So for all these measures, 0.5 is guessing, 1 is a perfect score. So you can see our accuracy, or AUC, which I always see as a class-balanced accuracy, is, well, the accuracy is around 90%, the AUC is even 95%, so it's closing in on the perfect score. And if you look at the sensitivity and specificity, so the sensitivity in this case is the accuracy of the positive class, which in this case were the malignant tumours, and the specificity, the accuracy of the benign tumours, are also well above 0.5. So that looks quite okay. So now, of course, your next question is, okay, how would that compare to what we do currently? So how does that compare to radiologists? So we also asked a radiologist to manually score these patients. So on a 10-point scale, so 0 is very benign, or I'm very confident it's benign, and 10 it's I'm very confident it's malignant. So by using this scale, we can also make an ROC curve. So that's the blue curve you see over here. And you can see that, well, our method is pretty close to this blue curve. And also if you look at the performance in terms of AUC, it's pretty similar. You can see that the radiologist is actually a little bit better in scoring the malignant cases, which is also reflected by the fact that the radiologist has some points over here, which we cannot address. But our method is a little bit better in terms of specificity, so in classifying the benign cases. So then I can already go to my conclusion. So from this we can conclude that radiomics can indeed be used as a biomarker for this classification of primary liver tumors into malignant or benign, because the performance is similar to the radiologist. So the benefit of this is that you only need a T2 MRI, no biopsies, and in this case no additional sequences. And by training and testing it on this heterogeneous dataset, our model has already seen quite some different sequences from different hospitals, so we're pretty confident it will also work on various sequences from other hospitals. So some acknowledgements. And last but not least, this radiomics platform that I'm using in here is completely open source, and we try to make it very easy to use with some manuals and documentations. So if you want to give it a try on your own study, yeah, please look in here. And also we're continuously looking for more data to improve our model and evaluate our model. So if you're also working on something similar, please contact me. Thank you.